Next topic is analysis of cylinder pressure data. Cylinder pressure changes with crank angles as a result of cylinder volume change, and then combustion for sure, heat transfer to the chamber walls, flow into and out of a crevice region, and leakage. And all of these parameters influencing the cylinder pressure, the first two parameters, which is the cylinder volume change and combustion, has the largest impact to the cylinder pressure. And the cylinder pressure can be measured easily using a pressure transducer, for example, like a piezoelectric pressure transducer. In the other side, combustion, which is kind of the chemical process and result in the release or the conversion of chemical energy into the thermal energy, it cannot be measured directly. So in this case, we use the pressure data to get the information for the combustion process. And we can use the thermodynamic analysis that we just talked about in the previous slide to have the combustion information from the measured pressure inside the cylinder. This figure is showing an example of the cylinder pressure. On the left side, the cylinder pressure is plotted as a function of a fraction of maximum volume. So we have a maximum fraction of 1 at this point. So this is when the piston is at bottom dead center. We have the minimum fraction at this point. It is when the piston is at top dead center. And we have learned this PV diagram in chapter 2, 3, and so on. So we can identify in this case that we have a compression stroke following this line. And then at the end of the compression stroke, we have a combustion process, and then increases the cylinder pressure. And we have the maximum pressure here. Usually it's called peak cylinder pressure. And then the piston will move back toward bottom center, having an expansion stroke. On the right side, we have the PV diagram as well, but in this case, the axis, so vertical and horizontal axis, is in logarithmic basis. So we have log P for the vertical here, and then we have log V for the horizontal axis. So a good thing for this log P log V diagram is that we have a straight line representing the compression stroke, and then as the slope change, we have a combustion process, and then similarly we also have a straight line to represent the expansion stroke. So how can we get this straight line to represent this compression and expansion stroke in the log P log V diagram? So we can model the compression stroke and expansion stroke as a polytropic process. And in Thermo 1 or Thermo 2, you know that the polytropic process is represented by this formula. PV to the power of n equal to constant. So n here is the polytropic exponent. So for the compression stroke, it might be around 1.3, and then for the expansion stroke, it can be around 1.33. So n here equal to gamma. So this is the specific heat ratio. So if we modified this polytropic equation slightly, so we put a log here, so we have a log PV to the power of n equal to log k, okay, and then we have a log P, okay, plus log V to the power of n equal to log k, okay. And then let me continue at the bottom here. So in this case, I can write it down as log P equals to log k, okay, minus n log V. So you can see in here that log P has a linear correlation with log V, okay? And N now is the slope of this straight line. And this is very important, especially when we want to check whether the compression and expansion stroke is plausible or not. So by checking whether the line is a straight line or it's showing a kind of bending feature. Now let's take a look again on the thermodynamic analysis of the system inside the combustion chamber. So the thermodynamic system is shown in this schematic. The system boundary is represented by the dashed line, so this one. And then there will be a fuel coming into the system, assuming if it is GDI or it is diesel engine. Some of the energy will be transferred out of the system as the wall heat transfer through the liner, piston, cylinder head. Some of the chemical energy will be used to produce mechanical work that is transferred to the piston. Some of the energy will flow out of this system through the crevice, which is the blow-by. If we apply the energy conservation to this thermodynamic system, then we will have equation 9.24. On the left side, we have the chemical energy release. On the right side, this is the distribution of this energy. So the first term here is the change of the system internal energy. This is the heat transfer through the wall. This is the mechanical work transferred to the piston. And this one is the net energy flow in and out of the system. So fuel energy flow and then blow-by flow and so on. By assuming an ideal gas equation of state and make some modification of each term, we will have equation 9.27. In this case, we have the chemical energy again on the left side, but this one now is a function of the crank angle, so it is the energy rate. And then on the right side, you have a several term here. So what I want to show you here is that if we move this last term to the left side, so it's mean here we have, let me write it down here, we have a dqht, so this is the wall heat transfer over d theta, so this is minus and then plus. So on the left side you have the net energy release, so it's mean here is the difference between the chemical energy and the wall heat transfer. And this one is usually called as apparent heat release rate, okay? Apparent heat release rate. So this one is apparent. So we'll talk about this apparent heat release rate in chapter 10 as well. So the term on the right side here, you can see there it is a gamma, we have pressure, we have volume, and then temperature. So this parameter can be obtained from the test data. For sure, we need to convert this temperature into the other parameter that can be measured from the testing of the engine. So it is this apparent heat release rate that is obtained from the testing. So by measuring the cylinder pressure, then we can estimate the apparent heat release rate. This feature is showing an example of the result of the heat release analysis. You can see there the chemical energy release is distributed into different energy type here. So for sure we have the fuel energy maximum here. So let's say this one. The top line here is the fuel energy, and then you will have some inefficiency. So this one is the combustion efficiency. So it's mean, let me put a yellow here. So this yellow one represent the fraction of the unburned fuel or unburned hydrocarbon. So it's mean this is the fuel that will flow out of the engine along with the exhaust gas. So we have a high combustion efficiency inside the diesel engine because of the lean mixture combustion. We have a couple percent unburned hydrocarbon inside the gasoline engine. And then the next one, so represented by the dot, black dot here. So this one, let me put me select this and it's a purple. Okay, so this one represent the energy loss because of the blow-by. Okay, and then we have a decent fraction of the energy loss because of the wall heat transfer. And then the rest here, the lowest one here is showing the net heat release. So this one is in terms of the mechanical work. Okay, so this one is the P and plus the delta U. Okay, the change of the mixture internal energy. Okay, so this example of result can be obtained from the previous formula. Next topic is combustion process characteristic. The result of the heat release analysis from the previous slide is shown again at the bottom side of this slide. So as you can see on this figure is that the chemical energy or gross heat release curve have a kind of S shape. So you can see like this one, right? So you can see it's kind of like S shape. So the rate at which this fuel air mixture burn increases, you can see in this figure, from a low value immediately after the spark timing. So kind of like this one, it's showing a slow release, and then this reach a maximum rate at about halfway, so somewhere here, okay, through the burning process, and then it decreases close to zero as the combustion process ends. The definition that is commonly used to characterize this energy release aspect of combustion is shown in this slide. First, we have what is called flame development angle, delta theta d. So this is the crank angle interval between the spark discharge or the spark timing and the time when a small but significant fraction of this mass has burned or fuel energy has been released. So usually we use a fraction of 10% mass fraction burn to represent this flame development angle. And then the next one, we have what is called a rapid burning angle. So this is a delta theta b. So this is the crank angle interval required to burn the bulk of the charge. So usually we use the interval between 10% mass fraction burn and 90% mass fraction burn. So sometimes we write it down here as the MFB 1090, and this one we have MFB 10 or MFB 010. So okay, the next one is the overall burning angle, delta theta O here. So this is the duration of the overall burning process. So it is the sum of delta theta D and delta theta B. So this one is B. I think there's a typo in the book here. This picture is showing the schematic of the definition of flame development angle. So let's say we have a spark discharge or spark timing at this point. So let me put a red line. And then this one is showing the theta 10 or MFB 10. And then we have MFB 90, okay, at this point. And we have one more point here, which is the CA50. Okay, CA50 here is the 50% fuel burn timing. how do we quantify this combustion process when we discuss with our client or discuss with our co-worker? So we use two parameters to represent how good is the combustion process. So the first parameter, usually it's called MFB 1090. So as I mentioned to you in the previous slide, this represents the interval between CA10 and CA90. And then the second parameter that is used is what's called CA50. So this is the timing for the 50% mass fraction burn. So this one. So these two parameters is usually used to communicate with other people when we talk about the combustion process performance. So for sure, our goal is to have this MFB 1090 as short as possible. So it means we want to have a quick combustion process, and it is good from the thermodynamic perspective because it will increase the power of the engine. And then CA50 is used as a kind of the timing to have an optimum engine operating point. And you remember in the previous slide we talked about the MPT timing. So our target of the CA50 timing is usually the point that can produce the MPT timing. But for sure you cannot attain this MPT timing for all operating point because it is limited by the knock phenomena for the spark ignition engine. This feature is showing the net IMEP, so relative to the net IMEP at MPT timing. Okay, so therefore we have a maximum of 1 here, so which is at MPT timing. And this is plotted as a function of spark retard. So spark retard here is showing here as a function equals to current spark timing minus the spark timing at MPT, okay, at MPT timing. So when it is 0, so it means the spark timing is at spark timing is in such a way that it will produce the MPT timing. And then on the right side we have the same parameter for the vertical axis, but in this case the horizontal axis is the combustion retard. So it is the CA50 timing of the corresponding point minus the CA50 timing at MPT timing. So 0 here means once again we are at the MPT timing. As you can see clearly here, if we have MPT timing, it will produce the highest engine torque or engine power, and then any spark retard or spark advancement from this MPT timing will reduce the engine output torque or engine output power. How does the burn duration change with the engine speed? So we learned in chapter 7 and chapter 8 that as the engine speed increases, the piston speed increases, and it will increase the airflow, it will increase the turbulence. So in this case, the mixture burning rate or the combustion rate is strongly influenced by the engine speed. So because of this correlation, the combustion duration only increases slowly with increasing engine speed, and it is shown in this figure. So on the vertical axis, this is the combustion duration. So this is the 0 to 90% burn, and it is plotted as a function of engine speed. As you can see in here, it increases but slowly. So this should happen, so otherwise the engine would not be able to operate over the wide range of the speeds. So what does this mean? If we have 10-degree crank angle at 3000 RPM, so it is much shorter in real time than 10-degree crank angle at 1000 RPM. Okay, because at 3000 RPM the engine speed is 3 times than at 1000 RPM. So this characteristic should hold, okay? Otherwise, once again, the engine would not be able to operate over wide range of engine speed, for instance, like from 600 RPM to 6000 RPM. Next one, looking at the flame structure. I think we talked a bit about this flame structure in chapter 3. The combustion process inside the internal combustion engine occurs under turbulent condition. The combustion speed is governed by the laminar flame speed. So this laminar flame speed is a function of the fuel properties and thermodynamic properties. So it's function of the phi or lambda, and then EGR, and then pressure, temperature. The combustion speed, once again, is a function of the laminar flame speed and the turbulent condition. And the turbulent condition can enhance the flame speed 2 times, 3 times, 4 times, and so on. Okay, this figure is showing the schematic of the structure of the turbulent spark ignition engine flame. So we have a unburned mixture. So it is ahead of the flame front, and then we have the burns mixture behind the flame front, and this is the flame front. I put a orange color here, and as you can see in here, because of the turbulence, the flame front is wrinkled, and this flame wrinkling increases the interface between the flame front and the unburned mixture. And because of this interface increase, the combustion speed is increased as well. So we have SL here. So this is the laminar flame speed. As you can see in here, that locally the flame front still propagate at the laminar condition. So locally, okay. And then because of this flame wrinkling, the overall combustion process is increased. So we can write it down, the mass burning rate of the fuel as the m dot f equals to the density times the interface area times the SL. So this one is the total flame front area. We can also represent it as the rho times A. A here is a kind of the modeling A. So in this case, you can use A from the dash line. So this one, the dash line. So this is just kind of like the modeling A. Okay. And then, so I can put here as AL, for example. Okay. And then times ST. And ST here is the turbulent flame speed. And ST here is a function of SL. So SL is a function of the fuel properties and thermodynamic process. So ST here is a function of SL and turbulent level. And turbulent level is usually represented by the U prime, turbulent intensity. So because of this turbulent intensity, ST can be twice, 3 times, 4 times, 5 times of the SL. And we need this higher flame speed, because otherwise the combustion process cannot be completed at the end of the expansion stroke. This figure is just to give you an idea about the combustion regime location for the internal combustion engine when it is plotted. On the vertical side here is a function of the turbulent level normalized by the laminar flame speed, and on the horizontal axis here to represent the turbulent level. So I know this is too advanced to be introduced in this class, but for sure you will use this diagram. It's sometimes called Borghi diagram when you learn the combustion in advanced level. So what is the key point here is that the combustion process inside the internal combustion engine occurs under turbulent condition. So it means it is on the right side of this line, because on the left side we have the laminar combustion, and then it is also below this line. Okay, let me put a red line. Okay, so it means the turbulence is not that high that can break or can extinguish the flame. Okay, so it is at this location. So if we have too high turbulence, so the eddies can penetrate into the diffusion layer of the fuel and it can extinguish the flame. So at the end you will have a misfire. Okay, so once again, it is at this location usually we have the combustion process inside the internal combustion engine. Next topic is laminar flame speed, or LFS. So we talked about this LFS several times previously. So let's take a look on this LFS in more detail. So in this case we have laminar premix flames, and the LFS is used to characterize this laminar premix flame along with the laminar flame thickness, okay, delta L. Okay, so laminar flame speed, okay, is the velocity at which the flame propagates into quiescent unburned mixture ahead of the flame. So let's say I have the flame front here. Okay, so usually it's thin and it's regular, and then I have the burn gas, and then I have the unburned gas. So the velocity of this flame front toward the unburned mixture is called laminar flame speed. Okay, and the laminar flame speed is a function of the fuel properties. So in this case the fuel phi, and then for sure the molecular diffusion of the fuel and so on. It is also a function of the thermodynamic process inside the unburned mixture, so the pressure, temperature. The figure on the right side here is showing an example of the burning velocity or laminar flame speed as a function of fuel equivalent ratio. And you can see a different fuel in this diagram. So the laminar flame speed is maximum at slightly higher than 1. So it means it is at slightly rich mixture. So usually it's around 1.1. So we have this big laminar flame speed, okay, around this one. Okay, and because this laminar flame speed is fuel properties dependent, you expect having a different laminar flame speed for different fuel. For example, gasoline have this charge. Okay, so this is belong to gasoline, and then propane has a faster flame speed than gasoline. Okay, and then ethanol has the highest one here. Methane, where is methane? Oh, this one is methane. Okay, methane is in the middle side here. As you know that methane is the main component of natural gas. And then isooctane, that is usually used as the surrogate for the gasoline, is this one. Okay, so it's close to gasoline now. The laminar flame speed is strongly dependent on the temperature. So increasing temperature increases the laminar flame speed. Pressure has a minor impact on the laminar flame speed. And then you saw on the previous slide that the laminar flame speed is also strongly dependent on the equivalent ratio. So the laminar flame speed is maximum at phi around 1.1. Next one is, how does the burn gas influence the laminar flame speed? So we put a special topic on this burn gas because we use a EGR. So right now EGR is kind of the prominent option for reducing the emission. So we need to know how does this EGR influence the laminar flame speed. So when we talk about the EGR, we classify it as the burn gas. So we also have a different burn gas inside the engine, which is the residual. So this is the burn gas from the previous cycle. So how does this burn gas influence the laminar flame speed? So the presence of the burn gas in the unburned cylinder charge due to residual and any recycled exhaust gas causes a substantial reduction in the laminar flame speed. So this is because they reduce the heating value per unit mass of the mixture. And the feature on the right side here is showing the impact of the burn gas to the laminar flame speed. So we have the laminar flame speed here normalized by the laminar flame speed without the residual. So it's mean when it is 0, so it's mean it has no residual, it has no burn gas, sorry. And then the horizontal axis here is the mole fraction of the diluent, so which is the residual plus any recycled exhaust gas. As you can see in here, for any V, that the laminar flame speed decreases significantly with the increase of the burn gas. So the burn gas is used to control NOx. It can also used to increase the gamma. And from the thermal efficiency perspective, you saw that it increases the engine thermal efficiency. So you can check in the previous slide that the thermal efficiency of the engine increases with the compression ratio and the gamma. But having a higher burn gas will reduce the laminar flame speed significantly. So there is a limit for the EGR. Okay, otherwise you will have a misfire inside the engine. For GDI, the fuel is directly injected into the cylinder. So we inject the fuel during the intake stroke if we want to have a more homogeneous mixture. And we can also inject the fuel during the compression stroke if you want to have a stratified mixture. So in this case, we have a stoichiometric mixture around the spark plug and then Linz mixture far from the spark plug. So compared to the PFI, so this GDI will have a less homogeneous mixture. So in this case, we might have different flame propagation between the GDI and PFI. And then once back again to the stratified mixture, overall the mixture condition will be lean. So this is good from the thermal efficiency perspective because we will have less wall heat transfer, we will have a higher gamma, and thus increases the engine efficiency. And then to quantify the cyclic variation, we use the parameter what's called coefficient of variation in indicated mean effective pressure, COV-IMEP. Okay, it is represented following equation 9.59. So it is the standard deviation in IMEP divided by the mean IMEP, and it is usually expressed in percent, so it's multiplied by 100. So this define the cyclic variation in indicated work per cycle. Okay, and it has been found that we need to have maximum cyclic COV-IMEP of around 5% to have or to avoid a drivability problem of the vehicle. And these are three factors influence the cyclic variation. Number one here is the variation in gas motion in the cylinder, and then the variation in the amount of fuel, air, residual, and EGR. And the next one here is variation in mixture composition within the cylinder each cycle.